All participants are requested kindly mute their mic. We will shortly begin the session. Good afternoon, everyone. So, welcome again in this post-lunch session. In this session, Dr. Captain Ruturaj Singh will chair the session. So, I invite him to chair the session and uh, introduce today's guest.
Thank you, Eugene. So today's is now so this speaker of this session is Dr. Deepak Kumar Upadhyay. He is a postdoctoral fellow at the Faculty of Mathematical and Natural Sciences, Cardinal Stephen Wyszynski University, Poland. He did his PhD from Department of Physics, Department of Applied Physics, Faculty of Technology and Engineering, the Maharaja Sayajirao University of Baroda. He did MSc and BSc from Bharatpur University, Bhopal. He has worked as a assistant professor at Department of Applied Physics, Faculty of Technology and Engineering, Maharaja Sayajirao University of Baroda for a brief time. Then he has also worked as a teaching assistant from 2015 to 2020 as his tenure during PhD. His core area of research is condensed matter physics. His specific area of research is electronic structure calculation, lattice dynamics, and optical properties of the strongly correlated systems, metal oxides, and nanomaterials. High pressure studies, polymorph exploration, and crystallography of inorganic and compounds and minerals. He has received many awards and recognitions. He has published several articles in highly reputed journals. He has also presented his work in many national and international conferences, including India and abroad. So today he will be talking about the quantum espresso and the Burai softwares. So now I invite Dr. Upadhyay to please start the session.
Thank you, Dr. Rituraj. Am I audible?
Yeah.
Okay. So thank you for the kind introduction. And today I will be talking upon the density functional theory. So first session is dedicated to the theoretical basic theory of about density functional, and then it will be a hands-on training of quantum espresso and its GUI version that is called DURAI Burai. So let me share my screen. So we will first discuss about the density functional theory, its fundamental concept, and then we will go towards the hands-on training. Okay, I think the screen is visible to all of you.
Yes, sir, it is visible.
Okay, so starting towards how electronic structure calculation using density functional theory. So first of all, what is density functional theory? So the density functional theory,
Sorry, sir. By mistake, I have muted you. Can you please unmute?
okay, am I audible?
Yes, sir.
Okay, so now what is density functional theory? Density functional theory is a successful approach to calculate the ground state properties of many electron systems. Sometimes it is called many body problem also. It is also referred as first principle calculations. So the density functional theory, nothing but a solution of Schrodinger wave equation. We all of know that what is Schrodinger wave equation. So it is a many body Schrodinger wave equation. Sometimes it is referred as ab initio calculation. It is called density functional theory, first principle calculation, and sometimes it is called ab initio calculation. So the ab initio is a Latin word which means from the scratch or from the beginning. Why it is called first principle or ab initio? Because it doesn't require any empirical parameterization. It is a quantum mechanical method and require very less parameters. And what are the benefits? The density functional theory are more accurate than its previous theories, such as the Hartree-Fock method, post-Hartree-Fock methods, or many body interaction models. So who developed this theory? This theory is developed by Walter Kohn, who received 1998 Nobel Prize for chemistry. So what it can be done by density functional theories? We all know that the human civilization, the materials have played an important role in the evolution of human civilization. So first of all, if we're talking about the Stone Age, so we are depend on the material based on stone, then it goes to Bronze Age, Iron Age, and now our lives are depends on silicon-based materials. It means the semiconductor, and the future will be on quantum materials, such as the materials which are used in quantum computers or topological insulators, and all these exotic materials are there. So to investigate the properties of these materials, we need a theory which is more accurately predict the properties of materials, because in the laboratory sometimes it is impossible to explore the material with exotic properties, or we cannot go to the quantum levels in the laboratory using our experiments, because the experimental facilities are sometimes very costly and it is hard to create uh, the environment in the laboratory. So we need a theory in which we can predict the properties of materials, and then we can explore to the laboratory or in the real conditions. For example, if we are talking about the high temperature superconductors or the materials which are responsible for topological insulator or battery materials and many others such as nanomaterials or biomaterials. So why we need density functional theory? One of the examples is to, for example, we want to create the extreme condition environment such as earth interior. For example, if we are talking about the interior of the earth, it means earth interior is, we have to study the materials at a high pressure. For suppose we want to study the materials at 150 GPa. So it is very difficult to create this type of environment in laboratory. But using density functional theory, we can easily create the environment of 150 GPa or 360 GPa using density functional theory. So we can investigate the properties of materials at these conditions. which is high pressure and high temperature, which is impossible to create in laboratory. So we can find some novel properties such as the novel chemistry of nitrogen, novel chemistry of fluorides, how the materials can behave at these conditions. So these type of properties can easily be done by density functional theory. For example, if we are talking about uh, gallium nitrate crystal at high temperature and high pressure, so this type of phase diagram can also be done by density functional theory. Then we can, if we found some interesting properties, then we move towards the developing of material experimentally. Uh, if we want to create some pressure environment in laboratory, then we can use the diamond anvil cell also, which is the apparatus which applied the pressure for the materials. So now discuss about the theory, which theory is responsible for density functional theory. So it is nothing but a fundamental of first principle methods lies in quantum mechanics. It is a quantum mechanical theory which expresses the conduction of electrons and atomic nuclei. So this is the very famous Schrodinger equation, which is H psi is equal to E psi. We all know this equation where H is a Hamiltonian and psi is the wave function. And by solving this, we can derive the energy eigenstate in many body problems. The fundamentals of this theory begin at 1964, where Hornberg and Kohn developed two theorems. The first theorem states that in the systems having n interacting electrons, the many-body ground state wave function, such as psi wave function psi of n number of electrons, is a unique functional of electron density. In Schrodinger wave equation, if we goes to the traditional Schrodinger wave equation, we have to consider all electrons. But the first theorem of Hornberg and Kohn considered the electron as a functional of electron density. That's why it is called density functional theory. It is a functional of electron density. We consider all the electron as a homogeneous electronic gas. So this is referred to the functional of electron density. And the electron density can be represented as rho r. And these are the number of electrons. So according to the first theorem, the Hornberg-Kohn equation can be expressed as in this form. So we can find out the energy of the electron density, where VEE is the electron-electron repulsion, T is the sum of electronic kinetic energy, and VR is a function of nuclear potential energy. So this is the first theorem of Hornberg and Kohn, in which we can find out the energy state of electron density. And the second theorem describes the minimum principle, or sometimes it refers to the variational principle for the density, and propose that the ground state energy of any trial density refers to the rho TR, cannot be smaller than true ground state system. So it also can represent as the energy of trial density. So this is the famous paper at 1964, which is the first paper which describes the fundamentals of density functional theory. So this paper is published in Physical Review, and the title is Inhomogeneous Electron Gas. So the first paper of P. Hornberg and Walter Kohn. Walter Kohn received the Nobel Prize in 1998 for the chemistry for the development of density functional theory. Now, moving towards after the Hornberg and Kohn theorem, the Kohn-Sem theorem take place. So Kohn-Sem methods offer an approach to derive the information about energy, structure, and properties of atom and the molecules by introducing a fictitious supporting system to resemble the true many body electron system. So in this equation, the external term which is referred as EXC. EXC is the exchange correlation functional. So all of you are heard about the pseudo potential or the what we can say pseudo potential method and all that. So these external terms is added to the Cohn-Sem theorem. So the Cohn-Sem theorem is more accurate than the previous Hornberg-Cohn theorem because of the exchange correlation terms. So it describes the energy having correlation energy, exchange energy, and Coulomb correlation energy, and the self interaction correction. So these terms also added to the Cohn-Sem theorem. The Cohn-Sem theorem is a final equation in which we are using the density functional theory. So the density functional theory is based on this equation with the additional exchange correlation functionals. So this exchange correlation term is very important for density functional theory. So this is the Schrödinger view. We are consider all the electron interacting with each other, but the DFT view is we can consider the interacting electron as a electron density or inhomogeneous electron gas. So it is impossible to solve Schrödinger equation because it is for more than one electron, because it is costly, computationally too much costly and almost impossible. So using density functional theory, so we can easily calculate the properties, easily calculate the energy Hamiltonian using density functional theory. So this is the pioneer work of Hornberg and Cohn. For this, Walter Cohn received the Nobel Prize. Now, to solve this equation, several computational codes are there, and it can be solved by self-consistently. It means first it guessed the electron density, then they solve the equation. If he found the minimum electron density, so it can be done. If not, then again it will initial guess the density and then solve. So this is almost a self-consistent process. So we have to give the input first time, then it can be solved by self-consistent method. And also we have to provide the exchange correlation functions for our system, which I will discuss when we are doing the tutorial. So some of the example of exchange correlation functionals are local density approximation or generalized gradient approximation. So let's discuss briefly what are the exchange correlational functionals. So what are exchange correlation functions? First of all, one of the examples is that it has been observed a density functional theory calculation based on exchange correlation function to determine the band gap value of semiconductors, or to determine, in short, we can say to determine the true ground state energy. The true ground state energy depend on the exchange correlation functional. So first functional develop is local density approximation, which is called LDA. So as the name suggests, it locally consider the electrons. Then the modified version of LDA is generalized gradient approximation, that is GGA, then refers to meta GGA, hybrid functional, and many more approximation are there. So the approximation LDA is that for the charge density behaves locally, similar to the heterogeneous electron cloud. So as the name suggests, it considers the electron density locally. It is not very accurate functional, but people sometimes use this because it is computationally low costly. So what are the limitations? The limitations are that it considers the electron density as a localized function. Then the modified version of LDA is referred to the generalized gradient approximation. So to improve the accuracy of LDA, Another approximation known as GGA has been proposed, which used to variables electron density and its gradient, and it can be expressed by this equation. It considered the electron gas homogeneously. And the GGA is developed by these scientists, Purdue Wang, in 1991. And its short form is, we can say, PB or PW91. Then, if GGA cannot predict the ground state energy or band gap is overestimated or underestimated, so then we can also use the external Coulomb potential. External U term can be used. So we can provide the value of Coulomb potential to improve the properties. So it can be referred as a Hubbard U method, which deal with on-site Coulomb repulsion energy into any of the exchange correlations such as LDA or GGA. So it can be generally referred as LDA plus U or GGA plus U respectively. So what are the effects of different exchange correlation functional? So for example, here is an example. If we calculate the band gap of any material, which experimentally is approximately 3.4 using UV visible spectroscopy and 3.3 using X-ray spectroscopy. These two band gaps are experimentally observed. And what density functional theory can give you? It will give you around these value 0.7 using LDA, 0.83 using GGA, PV refers to GGA, then PV 0. It will goes to 3.4, which is close to the experimental value. Then if we are using hybrid functionals, which is referred to HSE, it will give you around 2.4. Then if we use LDA plus U, it will give you 1.1, which is vast agreement with the experimental value. Then other functionals are GW, SX. So if we want to calculate the electronic band structure or to compare with the experiment value, we have to check which functional gives the accurate value. So these are the significance of the functional to calculate the ground state energy or energy band gap.
So I have a question from previous slide.
Okay, this one
Before that also.
here.
Yes, this one. So this method, what we exactly do, because LDA, GGA in previous session also, in morning session also has described. So can you bit elaborate on Hubbard U method, what we exactly do?
Okay. I understand your question. First of all, the question is why Hubbard U?
Yes.
Why? Because, for example, if we are doing some calculations on the rare earth metals, in which the free electrons found in the f orbital, which is very far from the nucleus. Understand? If we are doing about d electron system or f electron system, in which the free electrons lies in f orbital or d orbital, which is very far from the nucleus. So the exchange correlation, for example, the LDA and GGA cannot precisely create the effect for f orbital or d orbital. So we need some external potential to uh, attract these electrons. It means the free electrons is very far from the nucleus. So for that reason, we are using the Hubbard U for the d electron and f electron systems. For example, rare earth, suppose you have lanthanum or mm, the rare earth material, or you have copper has the d electron, and other cobalt has the d electron. So these type of system, if you have copper in your system, cobalt in your system, lanthanum in your system, europium in your system, so these type of these are the complex materials in which the free electrons lies in the d orbital and f orbital of a system. So we need external potential u. So U can be done. I will show you when we are doing the hands-on training. So how can we apply, or how can we use the Hubbard U for this system? You understand why we are using this?
So to account for the distant electron that is very distant from the nucleus, that's why we are applying this correction.
Exactly.
It is also in the case of the rare third tri-terminal charge insulator compound EuT3 RT3 compound we used to say, where they are basically rare tritellurides.
Yes. We have to use for the rare earth or the strongly correlated materials also.
Sir, can we apply Hubbard parameter for s orbital also? Because in many transition metal oxide we apply Hubbard parameter for s orbital also. So it is
for the exactly for the oxide, it is very complicated to find out the real band gap or the real ground state energy. So for the oxide, we have to do much calculation using Hubbard U or some hybrid functional also. Oxide is very complex system for density functional theory.
sir, is there any authentic website where we find the correct Hubbard parameter for any metals or metal oxides? Or
See,
we can apply some ranges.
yes. I will explain you. Nowadays, we can what we can say, we can convert the Hubbard parameter. We can find out the Hubbard parameters using quantum espresso. Uh, the new version of quantum espresso allow you to find the real Hubbard value, Hubbard parameter value. For example, the copper for the copper metal, the Hubbard value U equal to 7 electron volts is enough, or 6 electron volt is enough to find out the real experimental band gap. So you can calculate which value is good for the system.
Okay, sir.
There is no website which can tell you that if you can put the atom name and it will give you the value of a Hubbard U, but you can convert the value using some hp.x, some
Yes, sir.
hp.x
And
or something like this.
and it is applicable only on a new version of quantum espresso. It means 7.2 version, or it can be used in 6.2.1.
No, it can be, I think, beyond 6.3 it is available.
Okay, sir.
Something called hp.x you can find out. And another thing you can do, you can optimize the structure using different value, and then you can plot the energy or energy band gap. If it is convert somewhere, if you put 5 electron volts, 6 electron volts, 7, 8, 9, 10, these you can put the value, and then you can see where it becomes the converge, where the energy is not changing. If
Okay.
you have the good computational facility, you can also find out these type of scheme you can apply. So using this, you can find out the true Hubbard U value. This is
Okay,
only I am discussing here only U. There are more parameters such as J. J is also there for magnetic system.
Yes, sir. Yes, sir.
U is there, J is there, and many more parameters. So you have to, if you want to calculate very precisely, then you have to give attention each and every parameters.
Okay, sir.
So
One
this
more.
is the yes.
What is do you mean by this strongly correlated system? When we say it is correlated, or it is not?
Strongly correlated means in which the oxide system mostly we can consider as a strongly correlated, in which the energy very much depend on the correlation of electrons, or the electrons states are overlapping to each other, that they are generally referred as strongly correlated systems.
So, is there any criteria to decide whether it is strongly correlated or not?
Now you can simply search what are the strongly correlated system. It will give you hundreds of examples of the materials which are referred as a strongly correlated, such as copper cobalt oxide, copper chromium oxide, or some of the oxide based perovskite or fluoride based perovskite. These all are referred as a strongly correlated system, in which the magnetic properties are also responsible for the true ground state energy.
Actually, when we are simulating some new material, then how we can know it is strongly correlated or not?
Okay, you are talking about if we search, if you are,
It means if we are simulated for new material, basically novel material.
so you have to, first of all, if you synthesize some new material, you have to characterize it using whether it is magnetic material or not. If it is not magnetic, then it is not characterized as a strongly correlated material. It mostly relate to the magnetic properties of the material, which is ferromagnetic, antiferromagnetic, or it is uh, something like that. You have to do some characterization, then you can say that it is strongly correlated or not. Such as the new compound which is called half Heisler compound. So they are generally referred as uh, strongly correlated materials.
Suppose I am just simulating new material just by own. I don't have experimental data, then I have to do it and trial like that.
No, if you synthesize some materials experimentally, first of all, we have to characterize it for one or two characterization. Then we can say something about these materials.
Actually, I am not talking about the experimentally I have synthesized the material. I am talking computationally. If I want to synthesize some material, basically, I can say like that.
Computationally, you can computationally, if you are doing some calculations, then you can say what are the materials and how can we characterize it, how can we find out the which category it belongs to.
Basically, we just computationally compute all these values depending whatever whatever parameter we are taking, all these things, and with these parameter we can report we have taken these parameter and we are getting these values like that.
See, if your material is magnetic and you are calculating without giving the spin polarization, and then you give the spin polarization value, so you find out that if you give the spin polarization, you find the minimum energy for the spin as compared to without spin. So first, at this condition, you can say that the material is magnetic, and also you can find out the magnetic moment. You understand?
Okay,
So you have to find the ground state using these parameters. So if, and you also find the magnetic moment and other value, then you can say it is strongly correlated or not, or something like that. Okay.
okay, sir.
I will
Excuse me. So,
okay.
what is a negative sign actually imply? Is does it mean that as the orbital number increases, the interaction becomes more of attractive rather than repulsive? So, in the EDC term, there is a negative sign. So, what does it imply, sir?
Oh, actually, I cannot comment on this. Sorry. We will discuss it later. Okay.
Sir, for a strongly correlated systems, what will we do, sir?
What will we do? Can you elaborate your question?
It may interrupt. Everyone, please save your question for the last after this talk, so it will be easy to discuss. Because most time, if you are interrupting them, session will not be able to complete within time. Right? Dr. Deepak, please continue.
Okay. So what are the available codes? So here are some codes in which we can calculate the electronic and ground state properties, in which the quantum espresso is free of cost. Here is a very famous code which is Viana ab initio simulation package, VAS, and many more. So these are the available codes which we can use to solve the density functional theory calculations. So here is the example of how the band structure depends on the exchange correlation function. So first of all, if we calculate this is the material which is a two-dimensional gallium oxyhydroxide. If we calculate the band gap using GGA, then the band gap value is 2.81 for the direct band gap. And if we use the hybrid functional, so then we can find out the 4.4 electron volt. So the difference is around 2 electron volt, and which is the hybrid functional is close to the experimental value. So these are the significance of using different exchange correlation functionals. Okay. So I briefly discussed the electronic structure theory as we have very less time. So the behavior of electrons in materials and how they are distributed in the real space. So the different energy levels from the main subject of electron band structure theory. So what we can tell by calculating the electronic band structures, that whether it is your system is metal, semiconductor, or insulator, and many other properties such as transport properties, magnetic, superconducting properties. These properties can be qualitatively discussed by calculating the electronic band structure. So this is the nearly free electrons model. So electrons not fully free, but moves in an effective weak periodic potential. So using the periodic boundary condition. So in crystal, this is the lattice constant A, and this is the crystal potential. So these are the bound charts. So we can calculate the energy using h cut square k square by 2m, where k is n lambda by A. So this is the nearly free electron model with the periodic boundary conditions, which is the basic theory of electronic structure calculations. So here is the in large scale, which is 1 by L scale, and this is the 1 by A. So these are the wave vector k, which depends on the lattice constant. So this type of, we can create the EK diagram, which is the fundamentals of electronic band structure calculations. So quickly moving towards the important terminology, which is Wigner-Zeit cell, Brillouin zone, and break plane. So briefly discuss these three things. What is Wigner-Zeit cell? Wigner-Zeit cell is a minimum cell, or we can refer as a primitive unit cell. If I think all of you know the density functional theory, so it is referred as a primitive unit cell, which we are considered to calculate the electronic band structure of any system. So a Wigner-Zeit cell is a smallest possible primitive unit cell. It can be created like this. And what is Brillouin zone? Brillouin zone, this is the Brillouin zone for FCC lattice. This is the first Brillouin zone. We can consider the point of the Brillouin zone, and then we can plot the electronic band structure or calculate the electronic band structure using this highly symmetric point. So this is the whole Brillouin zone, and then it refers to the first Brillouin zone. So we are considered the high symmetry point for the first Brillouin zone. So this is the first, second, and third Brilliant zone, but these are not relatable. Only the first Brilliant zone point we can consider for calculating the electronic band structure of a Wigner-Zeit cell or primitive unit cell, or we can say for the conventional unit cell. So this is the electronic band structure of gallium arsenide. This refers to the conduction band. This is valence band where the valence electrons are situated. This is the wave vector k, and the y-axis is the energy of electronic states in electron volts. So what is the direct and indirect band gap? If this is the valence band, this is the conduction band. If the highest of valence band, high, and the lowest of conduction band is meet towards the same wave vector k, so it is refers to the direct band gap. If the minima of conduction band and maxima of valence band meet at the different value of k, then it is refers to the indirect band gap. In other words, the smallest energy difference occur at the same momentum value. If the momentum of the electron is changed, then it is indirect band gap. If it is not changed, then it refers to the direct band gap. So to wind up, the band gap arises due to the periodicity of potential experienced by the electron. So here we have discussed the importance of density functional theory and about the exchange correlation functional. So I skip all these recent works. So we will finish here. Then we will move towards the hands-on tutorial. So that's all from my side. Now you can ask the questions.
Hello, sir.
Yes.
Which is, sir, madam, sir, which place we can use local density approximation? Can you explain actually?
See, if you are calculating very simple system, then you can use the LDA or GGA. Sometimes, if you are not dealing with some complex system, as I have talked earlier, then you can use, if you do not have the F electron or D electron, so then you can use the LDA or GGA.
Among of them, which is better will give accurate value? We can't say properly. We can do LDA and G.
See, the GGA is more accurate than LDA because it considers the generalized electron contribution. So for this, we can use the GGA. GGA is more accurate than LDA.
Okay.
Sir, I have a question. I am working for a metal oxide. If the cohesive energy is negative, then I proceed to this material, or positive also workable is applicable.
See, we are talking about cohesive energy, or we can say a formation energy, for example. So here I will show you some example. Here I have calculated the formation energy of some of the compounds and created the convector. So here the answer is it depends. The positive cohesive energy can also be possible. People are saying that the positive cohesive energy cannot be possible, but it can be possible. You can proceed if you are confident that you are finding the cohesive energy which is correct. You can process. You can proceed. It may be positive. Cohesive energy may be positive.
Okay. It means the negative shows the stability more, or a positive shows because
See. More stability is not a good term. Only the stability. If you find the -1, it is stable. If you find the -2 value, it is more stable. So there is nothing more stable kind of thing. If it is
Oh,
stable, it is not stable. More stable is not there. It is a
so
wrong
what is
term.
the meaning of, it means negative energy. अगर मेरे को नेगेटिव एनर्जी मिली इट्स मींस आई कैन शो के द मटेरियल इज स्टेबल एंड आई कैन वर्क ऑन दैट.
Yeah, negative energy sometimes replies to the rely to the stability of materials. Yes, if you got the negative cohesive energy, then you can say that material is stable in experimental conditions. And you have to verify by calculating suppose dynamical stability or the formation energy also. If you want to uh, confidently say that this my material is stable, then you can calculate the formation energy and the phonon dispersion curve, the dynamical stability. Hmm. And also you can find the formation energy. Uh, so we can say that here I have plotted the formation energy for the experimental counterparts, and here the computational counterparts, and I compare these both two and find that the materials are stable. Then we can say that.
Okay, okay, sir.
Mm-hmm.
Thank you, sir.
Any other questions?
Sir,
Excuse me, sir. Sir, I have another question. Can we find the charges on the atoms by the quantum espresso?
Yes.
How many charges are transferred from one atom to another atom? Is there any method to find?
Yes, we can calculate the charge density and charge transfer.
So charge density can't show how much electrons transfer from one atom to another atom.
Then you have to manually find out the charge transfer, which is called the load-in charge transfer or the Bader charge transfer. These two methods are there. So if you calculate the partial density of states, so from the partial density of state, you can find out the charge transfer. It is there in the output of the CDOS.
Okay, sir.
Hmm.
Thank you, sir.
So it will give you the charge of each and every atom. Then you have to find out the charge transfer, if it is any charge transfer to, if you have a adsorbate or something like that, you can find out from the partial density of states.
Okay,
sir,
thank you, sir.
I had a question, sir.
Mm-hmm.
Sir, for nanocomposites and all, how will be the approach? How can we find the band gap of nanocomposites?
If you have the structure, it means the composition of a nano composite, configuration of a nano composite, then the method is same. The calculation of electronic band structure method is same for all the species, such as it is nano composite, nano materials, bulk, or any other thing. So there is nothing change in the method.
Sir, what kind of approximation we can use, LD or GJ or a hybrid, which will be more suitable?
Again, I am saying that it depends on the specification of your materials, which atoms are there, the nanocomposite made of a simple, if it is a carbon nanocomposite, then you can use a GGA. Nothing more accurate is required for the carbon system. If it is oxide or very complicated, then you have to move towards the GGA plus U or hybrid functional. So
Okay,
it
sir.
will depend. You have to converse the value. You have to find out the true minima using a different exchange correlation.
Okay, sir.
Mm-hmm. Okay, so if any other question, otherwise we can move towards the
Sir, actually, I have a small doubt. Actually, you are showing that earth core, different temperature. So that how you are calculating that in using DFT actually, that thing I have doubt. Can you explain, just elaborate?
yes. We can simply optimize the structure at different pressure. You understand? Variable cell. This is there is a method called variable cell approach. So we press the cell. We if we use the pressure, suppose if we are using 10 GPa, then we put the value of a pressure. It is 10 GPa. Then we optimize the structure using variable cell. So then we can find out the ground state energy at different pressure.
Yes, sir. Okay, sir. Thank you.
Sir, why correlation is important?
Correlation is not, it is exchange correlation. It means the correlation of electrons. So it is important to accurately minimize the exchange correlation values. See, every metal has a different exchange correlation. So it is provided that if you are using copper, cobalt, and nickel, suppose in one system, so then you have to provide the exchange correlation for cobalt, copper, and nickel differently. Then it will give you the accurate value. So that's why the exchange correlation functions are very important and debatable in density functional theory.
Yes, sir. Sir, I have another question. I am working on thermoelectric material, MOS2. So, what kind of potential shall I use? Whether
Again,
GGA or hybrid?
most of the people are asking which exchange correlation, which pseudo potential I use, which pseudo potential I. It depends on, again I'm saying it depends on your system. You have to optimize it. You have to find out which pseudo potential give you the minimum value. If you are using LDA, you find some minus 10 electron volt minimum energy. If you are using GGA, you find minus 12. Then you have to find out that which is which will give you the minimum energy, which will give you the suppose lattice constant, good lattice constant, which is matching the experimental value. For example, you are talking about MOS, so you have to find out the very good experimental paper which will give you the lattice constant value. Then you compare with your optimized system using LDA, GGA, LDA plus U, GGA plus U, whatever you use. Then you can decide which pseudo potential you have to use.
Okay, sir.
Okay.
Thank you, sir.
So there is too many things to compare. So you calculate, then compare, then decide which pseudo potential you use, and you proceed further for the thermoelectric or any other calculations.
Sure, sir. Thank you, sir.
Okay.
Okay, so I think there are no more questions. So maybe Dr. Deepak, you may proceed for the next session or need a break?
I think I can proceed to the
Okay.
hands-on tutorial. So
Okay.
let me stop
Okay, sure.
sharing here, and then
Okay.
okay. So Here we are. So this is the GUI version of Quantum Espresso, which is referred to BURAI 1.3. This is Burai. So is it visible to all of you? And one more thing, all of you which are participating in hands-on tutorial, so you are successfully installed the Burai or not?
Installed.
Okay. So we are moving towards the example sections. Here is the my project and then example. Okay. So you can open it and go to the my project, and then you can find out these type of three files, which is first is CIF, PWX, SCF, and XYZ. CIF files are refers to crystallographic information file. PWSCF is plain wave self-consistent files, and XYZ is some other files, okay, which give you the XYZ values in this. So CIF file is more important and universal. If you are doing the XRD experiment and other characterization, then you can find out the CIF file. From XRD, you can generate the CIF file, and then you can use for the density functional theory calculations. So here are some examples. For example, aluminum CIF file, CaSO4 and other. Here we are doing the electronic structure calculations for silicon. Okay. So just open this. So this is the simple cubic structure of silicon. These are the silicon atoms. And we are going to the atoms. So these are the silicon atoms. These are the coordinates of silicon atom in the simple cubic unit cell. And these are the coordinates in angstrom. You can use also other units such as a lattice, Bohr, angstrom, or crystal coordinates. So you are seeing here too many atoms and only 8 are there. So it is due to the symmetry. This 0, 0, 0 is find out the four corner of a simple cubic. Then the second atom, third, fourth, fifth, sixth, seven, eight. So the atoms are arranged here in a simple cubic unit cell. So this is the structure of silicon. These are the atoms. Here is the element, which is silicon, and the mass of the silicon. This is the mass of a silicon atom, and this is the pseudo potential here. So we can choose another pseudo potential also. Here is the PB RRKJ dot UPF. So PB generally refers to the generalized gradient approximation, which is GGA. So here we are using the PB functional. And the other thing is Bravais lattice. So here is cubic. We can also, if you have different structure, then it is different Bravais lattice. And A is the lattice constant for the silicon structure. It is a cubic, that's why only A is showing here. Otherwise, if it is tetragonal or hexagonal, then it is A, B, C. Three lattice constant are there, and also the angle between them. If hello, okay, If you have any question, any doubt, you can ask between the tutorial. Okay. So these are the some parameters, lattice constant and the angle. If the angle is 90, then it is not showing here. If different, then we can see the angle value also. So first of all, this is the geometry of a system. This is a cell, then element, and then the atoms. So if we find out the geometry, then we first of all we have to optimize the structure. Okay. Optimization refers to the find out the minimum ground state energy of any system. So here the optimization process. So these are the parameters which are using for the optimization. So restart mode, if we are using first time and we don't have any XML or output file, then we have to put here no. We are starting from the scratch. So the restart mode is always no. Maximum time we can leave here. Then the variable cell approach. So I will optimize it using variable cell. It means the cell can also be changed. Variable cell means this cell is the boundaries of a cell. It can also be changed using the variable cell parameters. Then the convergence threshold, or sometimes it is refers to ions optimization. Okay, so this is the value. The method is DFGS. Then other method which used for MD, but here we are using DFT, so the DFGS method are there. Then the cell optimization threshold, we can put here 10 e raised to minus 3 because we have to calculate it in less time. So here we are using the less value for cell optimization. Here method is DFGS. Pressure, we are not applying any pressure. Somebody asks you how can you create pressure. So this is the tag for pressure. Here we use no pressure, so we put simply 0. And this is the 3-dimensional unit cell. We have to optimize it in all directions. So here we can put all. Okay.
So I have one question. What is this BFGS accounts for?
BFGS method, it refers to a method of optimization, which is BFGS. I will show you what is. It is a method which is Borden, Fletcher, and Shannon method, which is in short form we can say the BFGS. It is a method which can change the cell also. The variable cell method, it is a variable cell method which is by default we calculate using BFGS method.
Actually, I am asking in terms of whatever we are doing, we are solving the Schrodinger equation. Actually,
Yes.
So in that sense, to which term it just connect basically in Schrodinger equation, this kinetic energy, potential energy, exchange correlation, all these things are there. So this BFGS means what?
Actually, I have shown you the self-consistent method initially, algorithm for self-consistent method. So this is one of the kind of self-consistent method. DFGS is a self-consistent method to optimize the structure.
So it is based on the energy minimization, whatever we are.
Yes. It initial guess the density, then it will optimize it. If it is find the minimum electron density, so it is job done. Otherwise, it again starts. So this is the kind of method which is called BFGS. So two options are there. Well, first is BFGS, which is you can say DFT. Okay, for the instant you can say this is the DFT and this is MD. So BFGS is a density functional theory method. Okay.
So this is that you just introduced before this hands-on session, this whatever that you have introduced, that is incorporated in this in that BFGS.
Yes, exactly.
And second option, then so please show that option.
Which option?
In that box below the BFGS, there is another option.
This is the threshold cell
No,
optimization.
no. In method, if you
Okay,
click
this MD.
Yes.
This is the molecular dynamics. This is the molecular dynamics, which is semi-classical method.
Okay.
Understand? Okay. So these are the parameters for optimization. We can see here the input file also. So what we have done? We written here the calculation type of the calculation. Okay. So it will divide it in sections. First section is control. Here we can put which type of calculation we need. So we selected the variable cell method. Here we put yes. So we can find out yes.
Sorry to interrupt you, sir. So when we go in cell, so it says lattice constants and Bevis lattice, where under Bevis lattice we have the options of choosing simple cubic, face centered cubic, BCC, and all these. Okay, so is it so that for any element, for example, silicon, the lattice would be structure would be same, or can we choose it like which type of structure we want to choose for silicon?
No. We have no right to choose because
Yes.
silicon is simple cubic.
Simple cubic. So in case of silicon, why is it giving options of FCC, BCC, hexagonal, and everything else?
No, this is not for silicon. If you are using, for example, graphene, so you have to choose the hexagonal.
Okay. Because the name of the file was si.cif, so I thought it is for silicon.
No, the options are there. If you are using silicon, so it will give you this. For example, if what we can do, if okay, moving towards KNO3, for example. So the KNO3 automatically hexagonal and trigonal primitive.
Okay, it will come automatically whatever the structure is. Okay.
For the example, if you created your file, then you have to
I have to be aware of the structure.
Yes. And it will automatically recognize using your CIF file.
Okay. And what is meant by the first option, which is saying free FREE?
Free means
so that if we don't know the structure, then we can choose that.
No, you cannot choose. It is you have to know the structure first. So free is for if you are putting some atoms or you doing the molecular dynamic simulation, then you can put free here. Free for a box.
Free for a?
For a box or for a cell, simple cell.
Okay.
If you want to optimize some gas, for example, nitrogen in a box or 100 nitrogen atom in a box, so you can put here free. Otherwise, you have to put according to the CIF file. Okay.
Okay, sir. Thank you, sir.
So moving towards the optimization section, and we are discussing about the input file. So here the variable cell, it means it will relax using variable cell method. Then the convergence threshold. N step is the maximum steps of optimization. Here we put 100. You can also go towards 200 or 300 if your structure is not optimizing in 100 steps. Then the pseudo potential directory and restart mode is from scratch. Then this is the lattice constant, DGOS, cut value here, which is very, we put here around 100. And this is the number of atom is 8, type 1. It means there is only one type of atom, which is silicon. Then the occupation is smearing and the type of the smearing. Smearing is a electronic structure calculation parameter. You will go through it. Then convergence threshold, maximum electron steps and other things. And this is the ion dynamics method, which is DFGS. And then we have to define the cell and optimization freedom, which is all. And then K point. And this is the atomic number and the coordinates. So this is the simple input file for a optimization process. Okay, so we can simply run from here to optimize the structure. Save the project. I will save here in desktop. Now I will make some another SI1 example. And then there's the I'm running this on 4 processors and 1 thread. Okay, so it will start optimizing the structure, and here we can see the result. So this is the input file for optimization, and it starts to optimizing, and this is the output log file in which the iterations are begins, iteration 3, 4, 5, 6. Okay, so it will take some time to optimize the structure. Then we will discuss the results of optimization.
So I have
So
one question. This
you people
optimization.
are okay. Just one thing. You people are doing the example with me, or just you are just seeing the optimization and other things, or you are doing with
Trying to do as much as possible, but at times we are lagging. So we are hopeful that after we get the recordings, we will practice it again. But yes, at least to a large extent, that is applicable to me. I don't know about others,
Okay.
but I'm
So
trying my best
if you
to.
want, I can slowly do the things if
Yes,
you want.
slowly. Yes.
So you can also prepare the silicon file with me. Is
Okay.
it okay?
Okay.
Then
Okay.
and ask the question, and if you have any problem, because the aim is you people can also execute at least one system, so it will be beneficial, or there is some what we can say, it is useful.
So
Otherwise,
when we go with this geometry now, it is saying geometry SCF optimize MD DOS. So this band is energy band.
yes, this is the electronic band structure. Band
Okay.
is electronic band structure. So we will go from optimization, then SCF, and then band,
Okay.
and
Okay. So
lastly the DOS. So
okay.
this is the aim of this hands-on. So we can optimize the geometry and then calculate the band structure and density of state.
So what is meant by optimizing?
Optimizing means to find out the minimum ground state energy.
Okay.
Then what is the meaning of SCF?
Okay, SCF is self-consistent method. If we once optimize the structure, then we have to run the SCF file, which will give you the SCF is also refers to the optimization, but we for the electronic band structure calculation, we have to run the SCF, in which we will give you the number of bands also. I will show you once we moving towards SCF. Okay.
For the optimization, first we have to optimize the structure, then we have to do the SCF calculation.
Yes. I will show you step by step. First, we are optimizing the structure, and these are the results for the optimization. What we done? Okay, I think we have to go here. Okay, so I will show you what optimizations means. So this is the output file. Here we can see it is job done. Okay, so it optimized using the parameters, and it will take around 1 minute for silicon atom. So what are the output of this optimization? We can see here. Here the convergence of SCF. Optimization also referred as a SCF. SCF is a method, so nothing. So this is the total energy in red work. So we have to find out the energy. So this is the total energy for the 7 iterations. Okay, it optimized in 7 iterations, and this is the minimum energy. Then we can find out the force between the atoms. So this is the optimization. The force is minimum, then it second iteration it will go to high, then it is start to minimize the force between the atoms. So the total force is very less in number, then we can say that the structure is optimized. Okay, the aim of the optimization is to minimize the force between the atom, then we can say that the structure is true minimum structure. So this is the optimization of force. Then the lattice constant, it will go like this, and then it converts. So the lattice constant is 5.49. Experimentally, it is 5.44. Okay, so it is close to the experimental value. Then B and C are same. So and this is the optimization movie. What I've done, the cell is slightly expand. This is the original position, and after optimization, it slightly expands. So this is the final cell parameters and coordinates after optimization. Okay.
Excuse me, sir. Sir, I tried to run the input file after optimization, but actually it is showing some error. Actually, I'm not able to figure it out.
Okay, so you have to you have saved your project or not?
Yes,
you
sir.
must okay, so you go to the saved project and find out the crash. There is a file named crash. So open it and tell me what is written in this file.
Excuse me, sir. How you
Yes.
calculate the geometry optimization? Because after running, we get only SCF and log.scf and scf.ene.
Wow, what is that the log.output?
Log.output, scf.ene and in. But you have shown earlier that geometrical optimization graph for
This
lattice.
one. Oh, okay, this one. This graph you are talking about this?
No, sir, nothing is shown in the screen. Yes, sir.
Okay,
This
what is written in your log.output? If you find the job done or not?
the job done SCF is calculated and material is converged. SCF is converged in 8 iterations. Actually, I calculated WT.
What have you calculated?
Tungsten oxide, not silicon.
Okay, tungsten oxides you have calculated. Okay.
Yes,
So you have so many files, opt.ene, opt.force.
So you have not found the force and stress also?
No, sir, force, stress, lattice A.
Wait. You have run the optimization or the SCF calculation?
The SCF calculation. SCF calculation.
Okay, so start from optimization. You cannot, I think, run direct the SCF. For SCF, it will not show you the force and stress and lattice constant because in SCF, we are not optimizing the structure. We are just find out the energy. So it will not show you these things. See, the process is, first of all, you have to optimize, then run the SCF, then going through the DOS and other things.
So can you please repeat how to optimize by screen?
Sir,
You
in the
go,
crash file, it is showing the error is there.
what is the error? You can just put
So,
the error in chat section.
so it is not in particular, actually, it is writing that error hash, then 3 default by lattice vector 0 in crystal lattices. It is writing.
Actually, your voice is not clear to me. You can just simply paste the error in the chat box, then I will show you how to solve it. Okay. Now, if all of you optimize the structure, then the next thing is moving towards the SCF calculations. So first of all, okay, somebody asking that it will not give you the force or any other things, these things. So you can also, you have to put yes here, calculated force, calculate stress. Otherwise it will not calculate. Okay. So if you are doing
So
SCF,
what decides the number of iterations?
okay, number of iterations, generally by default you can put 100 iteration are enough for the system. If it
Okay.
not converts, then you can increase the number of iterations.
Okay.
Okay.
So basically, we have to put that number which gives us the convergence. It converges.
Yes.
Okay.
Yes. If it is not convergent 100 iteration, then you can increase.
Okay.
Somebody asked me previous that I cannot get the calculated force or calculated stress. So you can simply put yes here. Understand? So then you will get the force and stress value in SCF. Okay. So moving towards SCF, then these are the parameters. Restart mode is always no. Calculated force, yes, we need the force between the atoms. We also need the stress. What is the cut value, cutoff value? So here 25 Rydberg, which is okay for the instance because we need instant result. And this is only a tutorial. Cutoff radius. Okay. Yes. Okay. Then total charge. We are not putting any charge. Use symmetry. Yes. We are using the symmetry. And the K points are 2, 2, 2, which is okay. All these things are okay. Type of smearing is also important for electronic band structure calculation. Here we are using Gaussian for the instance and the width. Then electron optimization, maximum iteration. Here 200 is there. Threshold, we can just minimize the threshold because otherwise it will take time. So 10 raised to minus 4. Initial gas atomic plus random. Diagonalization David. And this we are not putting any value for.
So whatever option you are selecting, please explain why we are selecting all these options.
Okay. So this is simply the threshold. Okay. Threshold means 10 raised to minus 4. It means after the point, only 4 values are there. It means it will convert 10 e raised to minus 4. You can also increase the value if you want more accurate result. Here we are doing the tutorial and we have to run quickly. That's why I have selected 10 e raised to minus 4. Generally, the default value is minus 7. It means 0.7 times 0, then a value. If you get the same value from the 7th digit, it will converge your structure. So here I am just using -4. So this is the threshold value.
So
In
this
quantum,
is energy minimization.
yes. In quantum espresso, -7 is default, but I am using a less value because of the we have to run quickly. Okay, we have to see the result also here. So I put 4. 4 is not good. 4 is not good for the optimization. You have to put 7, -7. But here I just put 4. Then initial guess. So it is initial guess is atomic plus random. I have shown you previously the self-consistent method in which we are using the initial density. So this is the method for initial density guess. So this is atomic plus random. Diagonalization, 3 methods are there. Generally, the diagonalization David is more accurate and people are using. The CZ is called conjugate gradient approximation. So which can also be used, David or CZ. This RMM is not used by the people or it is not famous. So we can use David or CZ. So I'm using here diagonalization David. And then initial guess also atomic plus random, or this is for charge density. So these and other things are not important, or mixing method. Okay. So this is plain and other things are there. If you are using
diagonalization, why we require that?
Okay, it is a method of diagonalization. Okay, when we solve the self-consistent process, it is also two methods, two famous methods are there. One is David and another one is what we can say, the conjugate gradient approximation. Okay.
Okay. So
And then
okay.
Okay.
So please you complete them.
Okay. So moving towards the magnetization. If your system is magnetic, for example, silicon here is not magnetic, so I am not putting any spin polarization value, but I will show you how can you put the spin polarization for a magnetic system, or if you want, we can consider one example of magnetic material. So here, if your system is not magnetic, so you can simply put the non-polarized. If it is magnetic, you can put collinear. Okay, then you have to give the magnetization value, which is total magnetization, or if you want to give the magnetic moment for atom, then you can put the atomic. For example, if your structure is ferromagnetic, okay, just suppose gallium nitride, so you want to put the spin half for up spin for gallium and down spin for nitrogen, so you can put the value here, magnetization. So for spin half you can put 0.5 for one atom, and the second atom you can put -0.5 or so on. Okay, so in this way you can give the magnetization of an atom. Here for the instant I am not considering any.
So what is this non-collinear magnetization? When we
collinear means, non-collinear means it will give you the XYZ. You can give different direction, the magnetic moment at different direction. Okay. Collinear means in a single direction. Okay. So these are the difference between collinear and non-collinear. We are just non-polarized for the instant. And GGA plus U. If you want to use the U parameter, then you can also give some value here, for example 0.5 electron volt. So this, for the instance, I am not using this.
in
so
the
this
standard setting, actually I have some doubt. Please go on the standard setting first.
Okay, here. Okay.
So this cutoff work function and cutoff for charge. What is the meaning of all these things?
Cutoff work function, it is simply referred as E-cut value. You have to optimize it. What value you have to convert the value of E-cut. You understand? For example,
E-cut means
energy cutoff, the cutoff value in which the energy converges at some point. You can use different E-cut. For example, if here we are using 25 grid work, so you can start from 25 to 100, I can say, and then you see which after which value the energy is not changing. You have to optimize the cutoff value. Okay.
is that you have already given in this electronic optimization 10 power minus 4. That is this.
No. Which is the which is called threshold. Previously, the -4 value is threshold value, and
Okay.
this is the energy cutoff, E-cut.
For the system, for a given system.
For a given system, so you have to also optimize. You have to optimize three things. First is E-cut, then K points, and no, these two things, E-cut and K point, you have to optimize. You have to find out which value I have to give for the system. 25 read work is very less. You have to optimize this value. And
this
also,
cutoff of charge, why it comes in play?
what is your
Cutoff for
question?
charge. What we
Yeah.
Why we are
Cutoff for charge is not so important. Cutoff of wave function is important. Work function is not a good is right term. This is the cutoff of wave function, which we are using cutoff of size. Okay, wave function, and the charge is simply 4 times this. Okay, here is 25, here is 100. So it is always the 4 times of cutoff of wave function.
So
and
this
it
charge
is
is the electron density and what type of charge it is?
charge of electrons, obviously charge of electron density. Okay, and this is the cutoff of charge of wave function, cutoff of wave function, cutoff of charge, and it is 4 times to this value, and it is default. By default, it is 4 times. You have not to always put this value, but it is showing here. Okay.
Occupation smearing and smearing Gaussian. What is the meaning of these two words?
Okay, so for that, I will give you some here. Are you showing this input file description here? Is it visible? Input file description?
No, sir.
No? Okay, what we can do? Okay, for all these things, because these things are too many things are there, you can go to the Quantum Espresso page or the pw.x input. Okay, how can I show you? Okay, I just have to reshare this. Okay, is it visible? The input file description?
Yes, sir.
Yes, sir.
Okay, so you simply type in Google pw.x MIT. Okay, I will show you pw.x MIT, and this is the first link, input file description for pw.x. Okay, so here you can find out all these things. For example, which calculations? So calculation, what is SCF, NSCF, band, relax, molecular dynamics, variable cell MD, and the description of all these things. Okay, so there are too many things. You have to read all of the things. All the input parameters are described here. For example, you are asking about smearing or Hubbard U. So smearing, where can I find the smearing?
It is in between this in systems. Yes. It is.
Okay. Occupations. These are the occupations smearing. So these are the smearing methods. Smearing, Gaussian smearing, it is for method, for metals. If your system is metallic, then you can use Gaussian. Then the tetrahedra. Another method is this. This fixed smearing can also be used for insulating with a gap. So these are the description for different methods. So you can simply go here and find out the meaning
Actually,
of
it's
all the
not given
text.
here. What is the basically significance of the occupation and smearing? That is not described here. Here it is only described which
Parameter you have to use. Okay.
Yes.
So this is the aim of this tutorial. If you want to understand what is smearing, then you have to go through the textbook of the DFT, because this subject is very vast. Each and every parameter has their theory, different theory, okay, different equations and all these things. So you have to go through the textbook. Here only the conditions are written, which for which system you have to use which method. Okay.
So in one line, if you will describe what is occupation and what is smearing, then how you can describe it?
Actually, I cannot describe because it is a method of optimization. Different methods are there and they are described in this paper. For example, the tetrahedra, you can read this paper. Here is described. So these are the method of optimization, or what we can say, electronic structure calculation. Here we are only discussing the significance of this method. Yes, what is the question?
You are saying you are applying Hubbard parameter. Sir, I am using the material WOC in which I use the Hubbard parameter 6.2 Luxembourg. But as I type in W section 6.2 and go to the input file and save it, then it uh, disappear and already shows 0.000. So how can we apply Hubbard in Burai?
Okay, I
Can you
will show
please
you. Okay,
show
okay, okay.
by
So
the
now you understand how can you find out the significance of these parameters from here. So now I will go to the Burai section. Here. Okay. So now we are doing SCF calculations. Here, these things. And you are all asking about the GGA plus U. You can simply put yes here and provide the value of Hubbard parameters. Okay. For example, I will put here 0.5 and then see the input file. So we can find out the Hubbard parameter LDA plus U equal to true. Okay. So if LDA plus U equal to true is there, then we are using the Hubbard parameter. Okay. Understand?
But sir, it's not showing that you are applying 0.5 in the right section. And it's showing silicon is equal to 0.00, and in the input file it shows LDA plus U. What does it mean, sir?
No, here LDA plus U, you are right. It is not showing the value of Hubbard parameter. Just looking for the
It means
file.
that it is applied in the input file as we save the file.
Just okay, here it is 8.0 or simply write 8. Okay. And then see the input file, it is there or not. Oh, here it is. Hubbard parameter for silicon 8. You understand? This is the value. which we given here the 8 electron volt. So for the instant, we are not using this, we are not using this. And moving towards the optimal SCF calculation of silicon, just simply run the calculation, job type SCF and other things. What is the error?
Previously, I got like this type of error.
Okay, just see the crash file. What is written here? It is written that constraint atomic magnetize required N spin 2 or 4. It means I have put the magnetization value and I have to see. Non-polarization, okay. No. Okay. Now let's rerun the calculation. Again, I will put SI2. Okay. Now I think it is running. Okay. This is the output log. Okay. It is solved. Just I have to remove the magnetization from there because I have not specified any value for the magnetization. So just wait for the calculation.
Sir, so sorry to interrupt you, but I'm still unable to apply Hubbard correction in input file. It shows LDA plus U, but not showing like numerical value like that 8.0 or something else. So can you please repeat for me for Hubbard correction only? And I have also one question. Hubbard correction can apply for only single atom or oxides can also?
No, it can be
I
applied for
think this is
different atoms. It can be applied for different atoms.
So I have to apply for oxygen also, or only for tungsten I have to use.
What is your system? WO3.
Yes, sir.
Tungsten you have to apply it, and also for oxygen, I think you have to go through the literature. What is the value and whether it is
Bura is not taking.
what?
Sure, sir. So Bura is not taking the Hubbard correction. That's why I can't find how to calculate.
Okay, I will just show you. It is that this SPF is done for without Hubbard, and this is the
Yes, sir. SCF is done without Hubbard.
and this is the optimal iterations. Now just
Yes,
take
8
the
degrees.
example. Okay. I am now just taking the example with Hubbard parameter. Just go to GGA plus U. This is true, and I will put the value of 8, suppose 8 EV for silicon, and just rerun the calculation. Okay, error again. If you have any error, then what you can done for the instance, you reopen this and then save it to the different name. Just close this. Okay, and then moving towards SPF and eight point zero. Save and save it with 3. Okay, something.
So can we publish the Burai result data? It is
So
authentic.
yes. You can publish. It is authentic. It is it
So
is
somebody says the quantum
okay.
exposure, quantum exposure. So you
Now I understand your error, because we are using different pseudo potential in which the Hubbard parameters we cannot use. Okay, this pseudo
okay,
potential
sir.
not yet implemented. So we have to
Accepting
change
this
the
Hubbard
pseudo.
parameter.
We have to change the pseudo potential from here. Optimizations. Element, and this we have to change. I think we have to use PD or simple PD. I think we have to use, just give me a second. We have to use some old pseudo potential, I think. Okay, here I'm not going towards the details of pseudo potential. Your error is for tungsten oxide. I think it is related to the pseudo potential. So you have to change the pseudo potential. Different format you can use, and hope you can solve the error. If you
Okay,
not able to solve, then you can just simply write me. I will guide you separately.
okay. Thank you, sir.
Mm-hmm. So now we can see we have this type of error you can get if there is something error or some parameters are not matched. So we can see geometry optimization and SCF. Now moving towards the band structure calculation. So for the band structure calculations, the only things is we have to specify the number of bands. Okay, and the number of bands. How can we decide the number of bands? It can be decided by the SCF output. Here we can see it should be larger than the number of CONSAM states. Okay, the CONSAM state can be seen in the output of SCF file. Okay, so if you have suppose 4 CONSAM states, so you can put here the value which is larger than 4. So here we can, and it can be higher value, can be something like 30, 35 or 100 is also there, but it cannot be less than the number of CONSAM states which can be printed in the SCF. And symmetry of band is also, we can put yes, and this is the Brilliant zone point for a simple cubic, because silicon is simple cubic, so we can put all these high symmetry points and the grid also. So grid is 20, 20 is good, so we can just put the 20 and see the input file, what are the changes. So here calculation changes to the band, we are using band calculation. Then moving towards, we can just remove this for the instant, otherwise still component also we can remove, isin true, and this is the Brilliant zone point, and other things are same. So we just simply try to run this calculation. Again, it will show you some error, which is, I think, related to the Hubbard parameter. So I'll just simply okay. Oh, somebody asking whether we can publish the result using Burai. You can publish, it is a quantum espresso. But Burai is nothing but a GUI of quantum espresso. Okay, so if we are publishing the result using quantum espresso, so why cannot be published using Burai? Okay. So this is the output of bands. This will take some time to finish. Actually, many things we cannot perform using Burai, and if you want to do some phonon calculation which is not implemented in Burai, if you want to do some NEB or optical properties calculation, then you have to moving towards the Linux version of Quantum Espresso, because Burai is for only for the beginners. Okay, so main calculation we cannot do using Burai. Burai can just, it is a referred as a visualizing code. Okay, it is not much calculation can be done using Burai. So if you want to do some accurate or real calculation, then you should moving towards the you should move to Linux version of Quantum Express, where you can converse the things and other. Burai is very restricted. The aim of Burai is just to create the input file and the structure of the things which can further use for quantum espresso calculation. It will take some time, I think. Okay. Okay, I think we got the band structure for silicon. Okay, so after the calculation, you will find out that there is a folder called band, and you simply double click, and this is the band structure for silicon. Calculated band structure for silicon at the given wave vector, such as gamma, x, m, r. So just to see the band gap, what we can do, we can zoom it from -1 to 1. Okay, it marks also, we can put 0.1 here. Okay, okay, so this is the electronic band structure for silicon. Okay, so silicon, as we know, it is a semiconducting material. It is not a metal. If it metals, then the band should crosses the Fermi level. So here we can see the band gap around 0.3, because it is calculated using the maxima of valence band and minima of conduction band. So the distance between maxima of valence band and minima of conduction band can be characterized as a band gap of any material. So here we can see the band gap around 3.2 or 3.3 electron volt for silicon, and it is an indirect band gap because the minima of conduction band and maxima of valence band at different K points. Okay, so this is the indirect band gap semiconductor for silicon. So we can calculate using this. Now moving towards the, so you people can, anybody calculate the band structure or getting some errors? Okay, so I think we are moving towards the density of state calculation for this. So for density of state, we have to use more dense K points. So here 444 are there. So we can just simply put 6 here, because density of state, for the density of state, the K points are important. Number of bands are same, which we use for band structure calculation. Other things should be same. It cannot be changed. And this is the scale. So we can vary the scale in the step. Broadening is simple Gaussian. And just to calculate, we have to just run the density of state calculation. Okay. So after the calculation, you can find out the folder name as DOS and just double click and we can find out the electron density. Okay. So just again from -2 to 2, we can plot it and 0.1. Okay, so this is the electron density of states around the Fermi level. So we can say that it also shows the semiconducting nature with 0.3 electron volt band gap. 1 to 5. Okay. You can also, if you want the XY data and plot these density of state differently, so you can go to the folder which is SI4 and just find out the PDOS value for different orbitals, which is 1s or 2p for silicon or any other metal. And if you want to analyze the charge, you can also analyze the charge transfer or value of charge from these files. Okay, so this is the partial density of state for different orbitals, and you can also plot using different plotting software. Okay, so all the things you can find out from the folder if you want to further analyze the things. Now, if you have any questions regarding to the calculation, so you can ask.
Sir, whatever we are getting that band value and whatever that diagram, we will get in the folder, na, sir?
Yes, yes, you can
Can you,
find
sir,
out all these things from the saved folder in which you save the calculations. Okay, for example, you can find out the bands1.gnu file for XY data. So this is the XY data for band. So you can simply copy it and plot origin or any other plotting software. Okay.
So for optimization of U parameter, we have to like manually we have to do it and optimize it, right? Like we give one value, do the calculation, again we give another value, like that we have to do, right?
This is a very conventional method. Also, you can go to what I will show you. You can also in quantum espresso there is a hp.x. You can use the hp.x variables for the executables for optimizing or for finding the Hubbard parameters.
So can you repeat it?
I will show you. Just input file hp.x. So
Actually, I cannot see that.
okay, just I will share again this where it is this. Using this input file description of hp.x. So you can use the hp.x for the Hubbard parameter. It in version 7.2 you can find out the hp.x file in which you can you can find out the real value of Hubbard U parameter. Okay.
Yeah, okay.
So you should go through this. It cannot be done in Burai actually. You have to go to the Linux version of Quantum Espresso. Okay.
Okay. Okay, sir.
So here you can find out the Hubbard parameter. Actually, in the reference section, you will also find out the publication for this method. So using this, you can find out the real value of Hubbard U parameter. Okay.
So if you want to in between kill the job, just close that. That's all.
In Linux version, you can simply
In Burai?
In Burai, you just there is a symbol for a stop job, so you can stop the job from there. If we run some support DOS and we can stop somewhere, stop the calculation, I think, or simply you can close the window, so it will automatically stop. Okay.
For electronic properties, we can use Burai. But if we go to optical properties of any material, we have to use the Linux version of Quantum Espresso.
Yes. Burai is not
But
allowed for
Linux
the
version,
TDD.
the problem with the TDOS because of oxides. Can you help us? Because the codings are more difficult for oxide version.
For the Linux version.
Yes, sir.
So you have to install first install the Quantum Espresso in Linux PC, and then you have to calculate all other things.
Sir, I have calculated Bader charges and density of state and band structure also, but for not for a Hubbard correction, not with a Hubbard correction, but as we apply the Hubbard correction, the band gap will show the same value. So I changed the Hubbard parameter many times. Like first of all, I apply 4.0 or something else. Like, but it is not applicable. Like the Hubbard parameter is not working. Band gap shows the same value.
Okay, so you have to plot the lattice parameter. You have to plot the energy, then see if the lattice parameter, energy, and other things are changing or not. Then we can conclude.
No.
Nothing.
Oh.
Nothing is changing.
No, so band इलेक्ट्रॉन डेंसिटी निकाली है सर और पीडॉस निकाला है, बट सर उसमें कोई रिजल्ट जो है ना डिफरेंस नहीं मिल रहा है।
So what about the lattice constant? I'm talking about lattice constant first. The volume, the energy of a system.
तो उसमें एनर्जी कन्वर्ट नहीं हो रही है। जब मैंने उसको डिफरेंट डिफरेंट पैरामीटर पे दिया तो सर उसका वो पर्टिकुलर ग्राफ नहीं, वो स्लोप जैसा ग्राफ नहीं बन पा रहा है।
No.
I can mail you with my problem.
Okay, you can mail me the result, then I can comment on it.
Okay, sir. Thank you so much.
Okay.
So one more doubt, like how we can choose like a good this potential, because in quantum physics there are many pseudo potentials, right?
What is the question?
Like how to choose, like how to optimize this potential, like they are giving many potential pseudo potentials.
Okay, how to choose a right pseudo potential?
Yes.
Okay. So first of all, again I'm saying it will depend on your system. If your system is metallic and not very complex, so you can simply choose the GGA, TBE type pseudo potential. There is also ultra soft pseudo potential. So if you want more accurate results, then you can move towards the ultra soft. And for very complex system or something called, again, for f electron or d electron system, you can also use the Hubbard parameter. So to find out the real or accurate pseudo potential, first of all you have to search the literature what type of pseudo potential give the accurate value, because if your system is new but the atoms and the component, for example gallium, silicon, they are very much covered in literature, so you can find out from the literature that which pseudo potential can give the accurate results. Okay, and then if you write your paper, you can also refer to this publication and you can. Okay.
Okay, sir. Fine.
Sir, is it possible to make MOS2 as a layer like structure here using quantum Roy?
Yes, you can make the layer from this option. You can simply go to the builder. Just a second. Here. And here you can create the layer of any of the system. Okay. So this is the option. This is modular. You can also take the structure from using Miller indices. For example, 1, 1, 0. So this is the structure for 110 plane. You can find the plane also here. Okay.
So why we use the superset?
Generally, a supercell is nothing but a repetition of unit cell. Okay. So if you want to calculate some properties in which the supercell is required, for example, if you are calculating the phonon dispersion curve, in which you have to calculate the displacement of atom, so you require the supercell. Otherwise, supercell is not required for most of the calculations. Only for phonon dispersion curve and elastic constant, we can use supercell. Otherwise,
the main basically unit cell, if it is modifying, then if the periodicity of the lattice getting doubled or tripled, in that case we have to form after phase transition, then we have to form the supercell.
Yes, exactly. And if you are creating defects or other things, and for doping concentration, to maintaining the doping concentration, you have to go to the supercell model.
Sir, is it possible to produce MOS2, like on MOS2, I need to coat another polymer as layer.
Okay.
Is it possible, sir?
Yes, you can create. It is something like heterostructure. If you want to coat some polymer on MOS2, so you can create a structure or configuration using Burai, Quantum Espresso, Vesta, any of the structure creating software.
Oh.
Okay.
Okay, sir. And one more doubt, sir. I am planning to buy new laptop or a desktop for doing this kind of calculation, DFT. A hardware requirement I need, sir.
See.
Or best calculation.
First of all, you have to buy a Linux-based computer.
Okay,
I
sir.
suggest you, if you want to, if your purpose is for DFT calculation, then first of all you go to the Linux-based computer with some new configuration. Okay, Linux sir. 17 or something like that. And actually you cannot run the calculation on laptop. Most of the, if your simple calculation can be run on laptop, otherwise you need some workstation or cluster for the larger calculation.
Yes, sir.
So just buy a Linux-based laptop and you can calculate some small things on this computer.
So what's the size of RAM? Around 32 GB or 16 GB shall I use for minimum?
No, 16 GB is enough. For 16 GB is enough. It will not hang your laptop. Or in Linux-based computer, 16 GB is enough, I think. RAM.
Okay, sir. Thank you, sir.
Okay.
Actually, I have small doubt. So previously, Sista and Burai. Actually, I saw that this Sista, we have to know that coding system, and here we are not using any coding system. Actually, I don't. Actually, I am beginner. I don't know the Sista and Burai actually. But here I feel that we are easily calculated. But there we are using some coding like this. Sure.
Okay. See, Siesta and Burai. Burai is generally referred to Quantum Espresso. It is a graphical user interface of Quantum Espresso. So Siesta and Quantum Espresso both are the different software. So I think Burai is simple, so you can use it. Siesta also provides some benefits in terms of calculating the electrical conductivity, which is very useful in Siesta, which cannot be done in Quantum Espresso. In Quantum Espresso, if you want to calculate the electrical conductivity, so it is difficult, but in Siesta, we can easily calculate the conductivity and other solar cell related parameters. So these are the benefit of Siesta and drawback of Quantum Espresso, but Quantum Espresso and Burai is simple. So these are the difference.
Beginner who don't know the coding, the coding, that he can easily use the Burai actually, I feel today. But compared to
yes, you can use Burai, and also see what is the purpose of Burai. It creates the input file for Quantum Espresso. This is the sole purpose to creating a Burai. Okay, so you can understand the input file, and also for band structure and DOS calculation you can use it. Okay, so it is simple. You are right. Burai and Quantum Espresso is simple and easy for the beginner.
Sir, I want to know in Also it is similar, although it is paid, but this whatever complication wise, WASP also similar to quantum espresso, right?
See, here I am using WASP. Okay, so I think previously in my PhD, I have done calculations using quantum espresso, all the calculations, and here now I am doing my postdoc and I am using WASP. So for 2 years I am using WASP, and previous 4 to 5 years I have used quantum espresso. So for me, if you talking about WASP is paid actually, so you have to buy the license, or if you are doing PhD, so your group have the license of WASP. But WASP and quantum espresso, I did not find any difference. But in WASP, the things are more accurate and things are more simple, and we can calculate. We have no restriction for calculation. For example, if we are talking about the quantum espresso, so we cannot use the spin polarization calculation for Raman spectra. We cannot calculate the Raman spectra of metals. But in WASP, we can do anything. It means I have not faced any problem using WASP that we cannot done this, we cannot do this, we cannot do this by using this. But in quantum espresso, there are some restrictions. So WASP is it is paid, so it will provide you some more freedom to calculate anything.
Also in this Burai, there is no NEB calculation option.
No. NEB, phonon and other things are not implemented in. You have to go to, if you want to do some research, you have to go to the Linux version of quantum espresso. I am suggesting that if you want to do some research, you have to do some Linux based calculation.
Okay, so I can use the quantum espresso for NEB calculation, but I can't use this Burai for that calculation.
No, the NEB is not implemented in Burai.
Yes, NEB is not implemented here, but I can do that calculation using quantum espresso, but not using Burai. Right?
See, Burai is not. Burai is a GUI of quantum espresso. So
yes,
using Burai, you cannot calculate the NEB, but actually Burai is calculating the things using quantum espresso. Okay. So,
yes.
but the NEB is not implemented for the GUI version. Okay. Otherwise, Burai is calculating the band structure using quantum espresso code.
Yes.
Burai is not a code. Burai is only an interface. Okay. So if you write the publication, and
can we calculate that NEB using espresso?
Yes, you can calculate the NEB using espresso. If you are doing the catalytic properties of material, then you can definitely do it using espresso. But
So
in Linux base.
No, why we do this NEB calculation?
NEB calculation is for transition state calculation for the reaction. If you are aware of the catalytic properties such as hydrogen evaluation reaction or some oxygen evaluation reaction, or if you want to synthesize something. So if you want to see how the reaction goes, so you have to calculate the transition state. So for the transition state calculation, people are go to the nugged elastic band calculation, which is referred to NEB. Okay.
Actually, in one paper, I saw this charge and compound. So in that case, they have just reduced or basically manipulated the charge and stable distortion, and they performed the null elastic band calculation in that. So why they did like that?
I don't.
Energy per atom, they have performed that calculation just by reducing or basically by manipulating the charge and wave distortion in tellurium layer in RTE3.
Okay. So they must be calculated if there is layer, then I actually cannot comment on this because you can send me the publication, then
You
also.
have some idea about what is charge distribution? It is a periodic modulation of the charge. That is called charge density wave. So the amplitude of this, just if we reduce the distortion, then amplitude of this charge density wave reduces. It is like that. So they have performed the calculation by changing the distortion, basically the amplitude of charge density wave. At different amplitude of charge density wave, they have calculated they have performed the calculation. In that, they have calculated energy per atom like that. So basically, energy calculation they have performed. So why they this elastic band simulation? That because you told this for transition state. So this is kind of transition state. You are just because here also we are just changing the charge density distortion.
No, maybe they must have calculated for to see the effect of distortion on charge density. So how actually I cannot comment before seeing the publication. You can send me, then also can I comment on this. Actually, I'm not expert in NEV calculation. I just know the basic about that.
Yes.
Okay.
Yes. Actually, I have wondered, like, can we like model if some S plus, like some ions, like giving some extra charges?
Yes, we can provide the charge using of any of the atoms.
Meaning we will give extra number of electrons to the.
Yes. People are doing these type of calculations also, to giving some charge of a particular atom, and then calculate the properties. Then see how this charge affects on the system.
Okay. So like in where we have to modify that, like in input, we have to change the number of electrons.
Now there is an option called give the charge to the atom. So you can give the magnitude of a charge of a particular atom. It is simple to the, for example, we are giving the Hubbard U.
Yeah.
So similar to the Hubbard U, we can give the charge also for the particular atom.
Okay.
There is option in quantum espresso. So if we are calculating some molecule or some other things, we can give the charge.
Okay.
To create some
so
dipole.
if you are doing the calculation for some ions, then we have to take some supercells, like maybe some like some OH minus with extra electron should be absorbed on some layer. Then we have to take supercells, right, of the layer. I don't know.
Actually, not kind of supercell. Ions, it means it is a molecule. You are talking about the molecules.
Yeah.
So you have to put the molecules in a cell.
Yeah.
If it's not periodic. If it is periodic, then it must have a crystal structure. Then we have to define the IBREV. It is cubic, tetragonal, hexagonal, trigonal, something like that. If it is not periodic, then you can simply take a cell and then put your molecules, number of molecules. For example, CO2. So you can put some 10 CO2 molecule, 20 CO2 molecule, and do the calculations, which is done by a Gaussian or some, what we can say, Gromax. Some molecular dynamics calculations are there. If it is not periodic, then it is not good to use quantum espresso in these things. They are generally for periodic system.
Yeah.
Okay.
So yeah, so this giving the extra charge, can we do it in VAS?
Yeah, you can provide. Yeah, vast quantum espresso both. You can give the extra charge.
Oh, okay.
So from where we can give the extra charge in quantum espresso? Can you show?
Actually, let me check if we can do from Burai or. Just give me 1 second. Okay, so there is option called total charge in Burai. So we can provide the charge to the whole system. Okay.
So where it is? Can you share your screen, please?
Okay. So here is the total charge.
So
And
it
if
means
you
we can give here the extra charge and just to create ion from the neutral atom.
yes, to create some dipole or to create some charge on the system, we can give the total charge here. And it is also possible in Linux based. We can also provide some charge to the individual atom also, but it can be done, I think. Okay. Yes, total charge you can provide. Total charge plus 1 means 1 electron missing from the system, and total charge minus means 1 additional electron are there. Okay, so this is the significance of this total charge. If you put the value 1, then 1 electron is missing, and minus 1 is 1 electron is adding to the system.
So can we do like that simulation in this? Just we are adding electron to conduction band, but as a whole system, it is neutral. So can we do calculation like that?
No. It will. The charge is for total system. We cannot decide whether the electron goes. So what are the effects? You simply give the value 1 or minus 1, then see the effects of the electron where it will go. So then you have to go to the orbital analysis. Okay, what is the effect of this charge on the system? But your question is whether we can move the electrons to the valence band or conduction band. Then we cannot do this. This is not allowed. Okay, so now I think this is done for you. You people can practice it. If you have any problems, then you can simply mail me. I can reply you for the
Hello,
problem.
sir. Sir, can we import the data files for other molecules in Burai? Because only limited molecules and elements are given over there.
Yes, you can simply if you have XYZ file, then you can import, or if you have your CIF file, you can also import. These are just examples. Okay.
Okay.
So you can simply create your own file.
Okay. Or from internet, I can download it, right?
Yes, yes. Any of the database you can download.
CIF file format.
For molecules?
Yeah, for molecules, just like perovskite materials I'm talking about.
Just give me 1 second. I will show you how can you download the file. This is the database called materials project. So all of you are aware of this. So you can download from here. Okay. So this is for silicon. So if you want to download the CIF file of silicon, so you can download from here. Export, and these are the, if you want to CIF file, so you can download here. Postcar also for VAS, and other file you can also download from here. And if you want to, you can also search for other materials. Okay.
Sir, zip file can be downloaded from material project. Any other resources there to download zip file, or how to get zip file any by manually?
Okay, there is another database called COD, crystallographic open database, COD. You can download from here. Okay, COD or material project. COD is more reliable. A material project can also be good website to download the CIF file. For example, MOS2, MOSE2. What are the structure? These are the files. You can go for rhombohedral MOS2. You can simply click here and download the file from here. This is the rhombohedral MOS2. So the COD you can also download. So these two are the database. You can also go to AFlow, but these two are more reliable and more popular database to download the CIF file. Okay.
Hello, sir. Sir, can we do the doping analysis in Burai?
Yes, you can calculate up to the band structure or density of state for your doped system.
And sir, can you please show us how to add an atom, dopant atom, and do the analysis in short?
Simply you, for example, just take the silicon. So you can go to the geometry and here you can remove, for example, silicon to the germanium. So you can, for example, remove one atom from here. So put germanium here and the coordinates also. So it becomes something like that. Just I'm showing just informal example. It is not true, but you can do the doping like that. For doping concentration, you have to, for example, the doping concentration here is 1/8. Okay. So what is the percentage of the doping you can calculate, and you can simply do the, and you also put here these two atoms are there for silicon and germanium, and the two pseudo potentials are also there. So this type of manipulation doping you can do in Burai. Okay.
Okay, sir. Thank you.
Sir, I have a question. Sir, There is another resources to download save file except COD and materials project. Any other?
See, Aflow, I think one of the Aflow you can use AFLOW, or you can use the reference of uh, the paper. Aflow is also a good database for materials. Okay.
Please repeat the AFU.
Let me show you. Ruko. Here it is. Aflow. You can find out the globally available database for something like 35 large materials compounds and the calculated properties. Okay. So these three are there: materials project, COD, Aflow, and और भी बहुत सारे हैं, वो सर्च कर सकते थे.
Hello, sir. Sir, can we do the gas sensing analysis by this software?
Yes, you can do. You simply put your gas and find out the binding energy, adsorption energy, and all other things. You can perform the gas sensing.
Can you please show, sir, if you don't mind?
No, it is simple. For example, for gas sensing, if you have your substrate, for example, MOS2, then you have to put some gas on MOS2. So you just simply take a molecule and create the system, put the CO2 molecule at some distance and calculate the total energy of a system, and then proceed with the band structure and other calculations.
Okay, sir.
Okay. Okay, so I think this is enough for this tutorial. I think you people got some idea how to calculate the thing. If you have any questions, any doubts, so you can simply write me, so I will reply. Okay.
Okay, so
Thank you, sir.
thank you, Dr. Deepak. Yeah, so thank you, Dr. Deepak. It was a wonderful session. I must say it was very interactive and very informative. Though I am from other field of research, but I also enjoyed it. So, being from the like particle physics and nuclear physics, now I have learned about the DFT, many things like quantum espresso that we have told today, and it was very well prepared and very well delivered. So I hope our audience, our participants would have enjoyed a lot. So thank you so much once again. And so now we will move to the next session. So I think Kaushal will take over from here. Kaushal, are you there?
Yes, sir.
So please let us know what is the plan. So I think there is a tutorial section now, or assignment based on lectures 1 and 2.
Yes. So there is
Okay.
assignment section.
Okay. Then please go ahead from this.
Yes. So participants kind of if you have kind of a race, we have more than enough time. If you have
Yes, sir. We
required
can have.
10 minutes.
Yeah, we can have a 5 minute break or.
Okay.
10
Okay.
minutes.
So um, we will meet around 5. Okay, 5 p.m.
Yeah.
Okay, so let us start. this session. So this session is for the assignment on basis of first and second hands-on session. Okay. So in first session, we learn about a siesta. Okay, and in second session, we learn about kind of URI. It is also a quantum espresso. So I just want to know that how's your experiment or how's your feedback for this workshop, okay, for this for the 2 sessions. So please you can easy to share, feel free to share from the audience.
Sir, I think
Hello, sir.
Okay.
Yeah, please speak.
Yeah, please.
Hi, sir. Am I audible, sir?
Yes, you are audible.
Sir, I was working in experimental part, so this is the first time I got an exposure to DFT. So first of all, the first session about siesta that I have heard, the basic things discussed about DFT. Again, in the second session also, we got an idea about it. So now the theoretical part is more clear. And Burai I have installed. So I have used Burai to an extent. So that part I understood. But about CSS or Windows I have installed. So I don't have Linux. So that hands-on experience I didn't get. So that is the only limitation I had experienced. Otherwise, everything was good. Yeah, that's it, sir.
Okay, so for the siesta or in the siesta, because of Linux, okay, and you are using now Windows, so this is difficult for the approaching kind of siesta. Am I right?
Yes, sir. Linux I don't have.
Okay, but most probably, or many theoretical physicists are using kind of Linux system, okay, Linux operating system. So you have to familiar with it and get it. So in Dura, you can starting your research, okay, in primary level, and then after you have to switch over the Linux system, okay, and so we also we will provide you a recording of this session, and then you can easily find out, and also we will providing the email ID or contact number for the speaker Okay. So you can easily join with later. Okay.
Yes, sir. I have carefully watched the session. So I will install the Linux. Sir, one more doubt. Is that Ubuntu sufficient, or we have to particularly install Linux?
So there are many kind of way to find out, or you can install the Ubuntu in Windows. Okay, so this kind of a virtual box is there. One second. Okay, so there is some virtual box in Windows. Okay, and then also you can download or you can download Ubuntu in Windows and then use the Linux system. Okay, so there are many ways to use Linux operating system in your Windows. Okay,
Okay, sir. Okay, sir.
yeah, so this is not only a one method, this is a various method. Yeah, Captain sir.
Yes, sir.
Yeah, so I just want to comment few things. So, like, who are working on the experimental condensed matter physics or theoretical condensed matter physics or any field of science, so I would suggest them to use Linux. There are many advantages. So it is faster than like Windows. Mac is different thing. It is faster than Windows, and the other part is the Ubuntu is very user friendly. So, like other Linux version like Red Hat or Fedora or many others are there, they are a bit complicated, but Ubuntu is the most easiest operating system, Linux operating system. Easily downloadable. You can easily download from its website, hardly 2 GB or 3 GB files, then you can simply install dual boot mode, or as Kaushal said, that you can install like virtual box. That's also easy. So yeah, so I suggest that most of the researchers should switch to the Linux, so it will be easy for them also.
Yes, sir. Yes, sir. Yes, sir. Actually, I am from Kerala. So in our school days, we used to use Linux, and after that, now in Kerala, up to higher secondary level, they are using Ubuntu. So I am familiar with that.
Okay.
But when I come
Yeah,
to
so
when it
Ubuntu
comes to
sufficient.
research,
Ubuntu is sufficient. Yeah, yeah. Ubuntu is sufficient because Ubuntu has very vast community. So like it is open source, and most of the packages are based on the Ubuntu repository. Okay. So like if any software will run on Ubuntu very easily, so there won't be any problem. So Ubuntu is fine. Ubuntu is great.
okay, sir. Okay, sir. Thank you, sir.
Yeah, anyone
Yeah.
else who share kind of experience for today's workshop? So these feedbacks are very important for us for the further workshop. So please feel free to share your experience.
Good afternoon, sir. So I am Samaranjan Pradhan. I am also experimental background. This is my first time to listen about DFT, but in the starting section, I know some basic, but in system, how to operate everything, I am not get properly. Maybe I am beginner, that's why I can't understand. But second section, I understand clearly because there is no coding that like this, and how to plot also, that is easy step also I did also. So it is so I second section, I understand the DFT, basically what is happening, why you are using, some basic idea I got it.
Okay, so for the Fiesta, there is no GUI, okay, graphical user interface, but in Quantum Espresso, there is a kind of a GUI. It is called GUI. So in GUI, there is no coding, just put it kind of put it a switch and click on this and there, and you will get kind of the result. So it is very easy for the experimental people. Okay, but also if you have to if you have required kind of more you can say that phonon calculation and all this. Okay, so for that you have to do a coding in also in quantum express also. Okay, so there is a learning portion, and this is just starting. So Ura is a very good platform for the beginner level. Okay, and then we can move on the coding. Okay.
Yes, sir. Thank you, Rajesh. Thank you.
Sir, one more doubt, sir.
Yeah, please.
Sir, for tomorrow's session, we have to install Orca, right, sir? Or any other software?
So you have to download kind of bold strip. Okay, because
Uh,
because one more software is there, Win2K, but Win2K is a paid software. So if you have a Win2K paid version, then it's okay. So you will not requiring kind of downloading it or install it. But yes, Bootstrap you have to install.
okay, sir. I tried to install Orca, but Orca I have downloaded the three zip files, but it is actually uh, it is some 3 GBs each, 3 or 2.6 GBs each. So I find it difficult to install, maybe because of my laptop limitations, the hardware requirements. It doesn't meet. Maybe due to that.
Yes, exactly. So it's a very you can say that it's a very big software, but but all the you can say that bases and all the functionals are already in that particular Orca. Okay, So it is also easy from the view, right? Okay, it's very easy software, but it's very you can say that very heavy software. Okay, so you have to download all the three files, and uh, we will learn kind of. Okay, and also you have to install the Avogadro. There is some visualization software. Okay, and from this visualization software we have to kind of making mm, input file for the orca. Okay.
Hello, sir.
Okay, sir.
Yes, sir.
Sir, I have a question. Sir, is Win2K software is also available? Hello.
Win2K is also available, but it is a paid version. Okay, so you have
Sir, from where
cannot
we can get it?
I think it's you just search from the Google Win2K, and then you have to kind of purchase the software. Okay.
Yes, sir. In tomorrow's session, you are going to discuss about Win2K software, right?
Yes. Bilkul.
Okay, sir.
Yes. If you have any doubt or any query about
Yeah, question just for curiosity. What is the cost for Y2K? It is less or like it is
no, it's very high.
very high? Okay, so like institutional level, it will be free. I think institutional would have buy all this thing.
I
Yeah,
think
but
no.
uh,
It's a paid version.
yeah, no, paid version like institute can buy. Okay, like for an
Institute can
individual,
buy.
it will
Yes.
be too much. Yeah, for
Yes.
an individual, it will be difficult to buy, right?
Yes. Exactly.
Okay.
Okay, so let's start this assignment session. So I think in first session, in the CS, many you have a query kind of thing, or maybe you are not familiar with the with the Linux programming and Linux operating system. So I think we have to start over here, kind of assignment for the view, right? So I think you all the aware of the, or you can say that all the familiar of the view, right? Am I right?
Yes, sir. Yes, sir.
Okay, so let's do the calculation on the view, right? For the different you can say that structure. Okay, so please anyone can tell me a kind of in example folder. Okay, how many are there, and which are their element or structure in the example folder. Please go through the view, right, and open the example folder. So how many?
In CIF?
Yes, in CIF. Yes, in CIF.
10.
So there are 10 examples. Okay.
Yes, sir.
Okay. So which one is there? Kind of. Please give me a one, two name. Give me a name.
Aluminium, CaSO4, Cu3Au, iron, KNO3, magnesium aluminate oxide, NaCN, silicon, and TiO2, ZrO2.
Okay. So we are doing the kind of calculation of the aluminium. Okay. So please So now I am questioning you. What is the first step for the find out energy minimization energy and all? What is the first step? So open your aluminum CIF file and please tell me what is the first step.
To do the operation.
Sorry, Manoj. Hello.
Go to
Hello?
optimization.
Go to optimization.
Optimization. Okay. So now start your optimization for the aluminum. If you have done, so please write a message on the message or meeting chat.
Sir, what should be the threshold and pressure?
Sorry. Hello.
Sir, about threshold and pressure, cell optimization.
Threshold and pressure.
Yes, sir.
I think pressure is not kind of. One second. You can.
Yes.
So what is the value for the threshold and pressure? Please tell me.
No, I don't know. Actually, in second session, I could not.
Okay. So what you have kind of in that particular in second session, sir is I think working on the silicon. Am I right? Hello.
I guess. Hello.
Yes, sir.
Okay. Everyone goes silent, so okay. So better like for this assignment session, if you ask everyone to switch on their camera, so that people see their activity, what they are doing. So I guess because no one is responding.
Okay. Please on
So
your
in
camera.
sort of this is assignment thing, so people should be more kind of interactive, right?
Yes.
Also, we need like photo session for today's session, so that I think we missed. So you took the photo for like first session, or, no, like, before lunch?
Yeah, I took a screenshot
Oh,
meanwhile, but
okay.
not at the end. actually. I forgot.
Okay, like it's okay. Yeah. Yeah, so everyone, I request you please switch on your camera so we could interact. So, sir,
Yes, sir.
some network is, yeah.
No, there is no network issue from my side. Uh,
Okay.
so participants, can you, anyone can share your screen?
Yeah, very awesome.
Anyone?
You may take the names so then people can respond.
Yeah.
Yeah.
So Khushbu, please share your screen.
She's there or she left? I don't know.
Okay.
Khushbu Thakur. Okay.
Lakshita.
Yes, sir.
Okay. So I think Khushbu is presenting. Yes.
Okay.
So you have already find kind of optimization energy or not? No.
It's 0, 0.
Still not. Okay. So you have to submit your assignment, okay, till tomorrow night. Then and then you have to get a certificate. Okay. So remember this thing. Okay, very good. So there is a total energy is minus 16.56. Read first. So participant, are you getting the same energy or different? Okay,
Yeah, so the assignment will be sent to them?
No. Just
Like,
same process. Same process. We have to do into the aluminium for the aluminium.
okay. Like Khushbu is asking, it was a great session. Where we get the assignment? Okay. Then I think you can post in the group what is the assignment. Then it will be more
No,
easier.
I think okay. One second. Uh, please share your screen again, or anyone can share your screen.
Rahul Bhujbal, can you share your screen? Okay. Shangita Vishwanathan. Most of the people are not responding.
So it's okay. They have to, but they have to finish your assignment, okay, till tomorrow night, and submit in the Google form. Okay, so we will require, we will give you a Google form, and you have to just upload your kind of screenshot or picture, images, and all, or output file.
There are only total energy.
Yes. So in the Google form, we have to mention what kind of particular parameter or images you have to upload. Okay. So don't worry about it.
Actually, I don't know parameter, but sir, whatever told us that previously silicon, that parameter only that parameter I
So
type
that is enough. So that is enough. Okay.
uh, and I got the result. Maybe I showed you.
So that I feel it's very good. Okay. So Captain sir, we have to stop over here, maybe, because there is no response.
Okay. Okay, then fine. So after that, there's no nothing else to do for today. Let me see the time. Hmm, time schedule. Can you share the time schedule of the event? We can see.
Yes, sir. Tomorrow we'll start at 9 a.m.
Okay, tomorrow will start at 9 a.m. Okay, okay, okay. Great.
The assignment
So
will
for
provide a group.
Sorry.
Assignment will submitted on will posted on group.
Yes, yes, yes. In WhatsApp group.
Okay, sir.
okay, thank you everyone for joining. So today we end the session here, and please don't be late tomorrow. Session will start sharply at 9 a.m. Okay, so please be there. Okay, so thank you once again. Thank you, Kaushal. Thank you again for great effort. Thank you.
Thank you, sir.
Thank you, sir.